In this example, I'm going to use row operations to help make it easier to calculate the determinant of this 4x4 matrix. If I were going to calculate the determinant from the matrix in its current form here, then I can choose to write the cofactor expansion along any row or any column. So I'd probably choose this column because it has a 0. But it only has the 1 0. And so, for example, I start with 1 times, I'd have the determinant of this 3x3 matrix, which that then would have to be found using a cofactor expansion along a row or a column of this 3x3 matrix here. And then again for 2 more 3x3 matrices. So that would take quite a long time. So for a larger matrix like this, it is important to be able to use some row operations first and help make it easier to calculate the determinant. So I would use the row operations here, -2 times row 1 plus row 3. So I'm using the same operations I would use if I were if I wanted to solve a system. I'm going to try to get the reduced echelon form here. I'll also do, draw a little arrow here. I'll also do 3 times row 1 plus row 4. Okay, now I put this in parentheses. Now, both of those row operations, well, they both have the form where you're taking a non-zero multiple of another row and adding it to a certain row of the matrix. And that particular type of row operation does not change the value of the determinant. So the determinant of this matrix will equal the determinant of the matrix resulting from those row operations, which is this here. So we're leaving the first 2 rows unchanged. And I'm doing -2 times row 1 plus row 3. So I add -2, I add -6. So that's -1. I add -6 again, so this will be -2. I add -2 times 4 up here, so -8, so this is -11. Oops, okay. And then in the last row, so 3 times row 1 plus row 4, so 0. I add 9, 9 again, and add 12. Okay, so there's a pretty simple row operation we could apply here. If we add row 2 to row 3, we could get another 0. We want to get as many zeros as we can below the main diagonal. You don't necessarily have to work all the way to the reduced echelon form, but this row operation isn't too much trouble to perform, and it'll, like I said, get us closer to the reduced echelon form. So this row operation does not change the value of the determinant. So the determinant up above is equal to the determinant of this matrix that I'm about to write out. Okay, so we're changing row 3, sorry. Okay. So -5 and -11, so I have -16 here. Oops. Oh boy. Okay, sorry about that. And then okay, now I could do another row operation. I suppose I will. I'll do one more row operation here and work on getting rid of this entry right here. So -2, but anytime you feel comfortable taking the determinant of whatever matrix you're looking for, you don't necessarily have to work all the way to the row echelon form. So if I do -2 times row 2 and add that. Okay, so there's been a bit of a jump in the video there. I just didn't want this video to get too long with me just writing out row operations and rewriting the matrix. Okay, so what I've done now is -2 times row 2 plus row 4, and that resulted in this matrix here. These determinants, again, are equal. Anytime you do this sort of row operation, so non-zero multiple of another row added to a certain row, that does not change the value of the determinant. So all of these determinants are equal, since that's the only type of row operation I've used in this example, remember that if you swap rows, that changes the sign, so you need to multiply the determinant of your new matrix by -1 to keep the determinants equal. And if you just multiply a row by a non-zero number, that's going to give your determinant that same multiple. So you should put the reciprocal out front. Okay, but all of that is in the theorem in section 3.2, so you can read through that. So when I did this row operation, I ended up with a triangular matrix, which means, all right, so once we have all zeros below the main diagonal, then we can find the determinant by just taking the product of these entries along the main diagonal. So this is equal to the product. I mean, since there's a 0, I don't really need to write this out, but just to be clear. So this is 1 times 0 here times 4. But so the determinant in this case is 0.